So we will continue with the nucleophilic addition to carbonyl carbons. We've talked about the carbon nucleophiles, where there is a negative charge on the carbon and the carbanion as a nucleophile attacking on the carbonyl carbon. Now this class we will move on to the oxygen nucleophiles. Oxygen atom serves as a nucleophile to attack on the carbonyl carbon. The first reaction we will look at is called hydration. Hydration basically is the addition of water to the carbonyl group. The reaction will take place either under acidic or basic condition, and after the reaction, there will be two OH groups attached to the same carbon. We call this the hydrate of the aldehyde or the ketone. The acid or the base catalyst is required. Under neutral condition, the hydration pretty much won't take place. The mechanism for addition of water under acidic and basic condition will be slightly different. So let's take a look at the basic condition first. Under basic condition, we have hydroxide ion. And the oxygen in hydroxide ion will serve as the nucleophile. It has a negative charge, so it will attack on the positively charged carbonyl carbon. The carbonyl CO double bond will break. So we are making a carbon-oxygen bond. Please note that in the carbonyl group, in ketones or the aldehydes, the carbonyl carbon is sp2 hybridized, while after the nucleophilic addition, it becomes sp3 hybridized. So the geometry of the carbon changes from trigonoplanar to tetrahedron. And we also call this product after nucleophilic addition as the tetrahedron intermediate. Okay, so next step, the O minus will pick up a proton from the solution, from water, to become the hydrate. Two OH groups attached to the same carbon. You need to make a note here that when we have two OH groups attached to the same carbon, these are not alcohols. They have completely different property compared to alcohols. They are the hydrates of ketones or the aldehydes. Again, under basic condition, hydroxide is a nucleophile. Because hydroxide has a negative charge, so it's a better nucleophile than the neutral water molecule. Now let's move on to acidic condition for hydrate formation. Under acidic condition, the first step will always be protonation. So the oxygen of the carbonyl will be protonated by the acid. The second step, water serves as the nucleophile to attack on the carbon of the protonated carbonyl. This step will form the tetrahedron intermediate. And the last step, deprotonation. Another water molecule will deprotonate the proton on the oxygen to give the hydrate, where the two OH groups attach to the same carbon. So as I mentioned just now, water as a neutral molecule, it's a weaker nucleophile. Generally, water will not react with carbonyl if it's just a C double bond O. When the carbonyl is protonated, it's being activated. Okay, so protonated carbonyl, we call it's the activated carbonyl. Why? Because we can draw a resonance structure for this protonated carbonyl where we change the CO double bond to single bond, and there will be a positive charge on the carbon. So the carbon and the oxygen will share the positive charge, which means the carbonyl carbon is more positively charged. It has more partial positive charges. So it's activated toward an attack by a weaker nucleophile, a neutral water molecule. All right. So compared to basic condition, we have stronger nucleophile hydroxide. So the neutral carbonyl will react. Acidic condition, the nucleophile is weaker. So we need activated carbonyl. All right. And generally speaking, aldehydes will be more reactive than ketones toward nucleophilic addition to carbonyl carbon. This is true for two reasons. The first one is the electronic reason. The difference between aldehydes and the ketones are what's attached to the carbonyl, right? For aldehydes, there will be at least one hydrogen attached to the carbonyl, and for ketone, we have alkyl groups, carbons attached to the carbonyl. We've learned before that alkyl groups are electron donating. Carbonyl carbon has the partial positive charge, and because it's positive, it can be attacked by nucleophile. While if we have alkyl groups, two alkyl groups like in ketone that are electron donating, which can stabilize the partial positive charge on the carbon, it can stabilize the carbonyl, which means the carbonyl is less positive and it's less reactive toward a nucleophile. So the ketone carbonyl is more stable and less reactive. It will react less. The second reason is the steric effect. Alkyl groups are bigger than hydrogens, so they are crowding, which will make the attack on the carbonyl carbon less efficient. They will shield or they will cover the carbonyl carbon, right? So both the electronic effect and the steric effect favors the nucleophilic attack on the aldehydes carbonyl. Electronic reason is the dominant reason here. All right. As a result, the hydration of the aldehyde is greater than that of a ketone. So under either acidic or basic condition, we will have more hydrates formed for an aldehyde, but for ketone, much less hydrates. And also, hydration is under equilibrium, which means it can go back to give the carbonyl. The hydrates are actually not very stable. The stable form is the carbonyl. So generally, you will not have hydrates as the final product of a reaction. Often, the ketones or the aldehydes will be the final products.